You have had a rough week, but I think you had all voted for this being the lesser of the two evils. The other one being your quarterly being today. I just want to remind you the quarterly is on Wednesday. It is the final quarter 2 grade, and it does replace your lowest regular exam grade for the quarter. So it can count as either 1 test grade or 2 test grades. In the grade book. And I do want to also bring up the thresholds. I have mapped those out. I will be sending on Monday when I am able to weed through the test exactly how many points are on each topic, and I'll also bring that up in tutoring. Like by topic, I mean by unit. Like I'll tell you how many points there are in unit 1, 2, 3, 4, and 5, the current one. A is 37. That's where Cambridge set the A mark at. And B 33, C 29, D 24, and E is 20. That's out of 60 marks. So those are the thresholds. Remember that these are, you have to earn the Cambridge mark to get it. So 37 Cambridge marks out of 60 possible marks is where the A level is set. You'll know that I'm going to grade it same day in the nighttime. I'll just get some extra coffee. And so I will be putting those numbers in the grade book, 120, 110, 100, 85, or 70. That translate to whatever it is. And if don't make the 20, then it will be tiered down below that. So if you get less than a 70 in the grade book, that means you did get a U on it. But I'm hoping that everybody doesn't U. Is that the goal? So let's go ahead and get started with today's lesson. I was also looking through the Cambridge exam, and I noticed there were, I don't want to give you the exact number of points, but there were some points on the lesson that we're doing today. They're like, it's not a ton, it's like maybe 4 or 5. Just to give you an idea, out of the 60 points, 4 or 5 will be on today's lesson. So yes. Here we go. Let's get to the objectives. So what are we being asked to do? We're going to define and use the term standard conditions. This syllabus, Cambridge is telling us to assume that our standard conditions for elements and compounds are 298 Kelvin. That's actually 25 degrees Celsius. Didn't we just do a lab? Do you remember how many Celsius the room was?
60.
Are we at standard conditions in this room? You know, when we do the paper 3, we have to send Cambridge what the temperature is in the room because that actually affects the results, by the way. But standard conditions are defined as 25 degrees Celsius. That's like somewhere in the 70s, like a 77 degrees. We are way colder than that in here. We're in the 60s. This is not the coldest classroom in the school. And 101 kilopascals. Or 1 atmosphere. And then what you need to notice here is notice this right here. This designation means that what you have is that standard state. So you see that little, looks like a 0 with a line through it? That is communicating to you standard state. It's standard state. So, sure, standard state. Enthalpy change with particular reference to, we gotta know what is the definition and how to use enthalpy of reaction, enthalpy of formation, enthalpy of boom, combustion, right? Boom. And then finally one that we actually already looked at. So I'm really not going to spend time on neutralization today because we actually already did define and do the math for that one. But we're going to be looking at the other 3. Formation, combustion, and reaction. Not really. They're just have different definitions slightly. Learning objective 5.2.1. Apply. That means do what you got to do, right? Apply Hess's law. Didn't you just hear about that? Hess's law to construct what? That's Cambridge's wording, not mine. Simple energy cycles. So you'll learn what Cambridge thinks is simple. Simple energy cycles. And I'll try to make it as not terrible as possible. And then learning objective 5.2.2. What is that? Carry out calculations. It means do the math, right? So you're going to have to calculate enthalpy changes that unfortunately some reactions you can't do the experiment for. So you can't calculate the delta H for every single reaction via calorimetry. There are some where you can't, like gas phase reactions. You can't calculate their delta H with a foam cup because it's in the gas phase. So if you cannot, by direct experiment, come up with the enthalpy change, you're going to have to be able to get the enthalpy change with Hess's law. And that's what we're going to learn how to do today. All right, so that's it. That's what we got to do. Hess's law. So this is an application of the law of conservation of energy. And I thought it was very interesting that Hank Green had brought up. Actually, Hess's law came before the law of conservation of energy. Hess's law led to the law of conservation of energy, which is the first law of thermodynamics, that energy cannot be created or destroyed. It's the same as the law of conservation of mass, except you switch the word mass for energy. So what is it? Energy cannot be?
Energy is.
No. Energy is mass times speed of light squared, right? Yeah. That's not for this class. That's physics again. But energy cannot be created or destroyed. But physical chemistry, which is the unit we're really in right now, it's called physical chemistry. There's physics in here, like it's there. Physics ideas are here. Energy cannot be created or destroyed. Good so far?
Yep.
All right. So standard states. Oh, recall these. Remember what unit did I ask you to do? This like unit 3, right? So do it again. Memorize the following. Know what your gases are, know what your liquids are, know what your diatomic elements are, right? Your diatomic, your monatomic, your polyatomics. You've got to be able to recognize an element in it. Standard state. That's going to be super, super important. Do you need a quick review? You remember that your diatomic elements are here. Only 2 polyatomics, phosphorus and sulfur. Everything else exists as 1. All right, so then what is enthalpy itself? Enthalpy we have spent some time on. It is the amount of energy. So it's the total energy associated with whatever materials you have that are reacting. However, it was mentioned you can't actually measure the enthalpy of like the chemical bonds themselves, like all the energy that's there. We can only measure the change in enthalpy, right? So that means we can measure the enthalpy of the reactants, the enthalpies of formation of reactants, and the enthalpies of formation. And this should actually have a little circle there, so you may want to add that in because everything's at standard state. The enthalpy of formation of the products and the enthalpy of formation of the reactants. And to find the enthalpy of the overall reaction, you actually just have to subtract the total amount of energy of your product and the total amount of energy of your reactants and subtract them. Well, you know, math, physics, and chemistry are all physical sciences are interrelated with math. Like it's all intertwined. It's just focus is different, if that makes sense. But you see the same symbols. All right, definition time. Unfortunately, yes, that is the end of that segment. Unfortunately, you have to memorize all the different types of enthalpy because there's a chance you get a 2-point question. What is the standard enthalpy of blah, blah, blah? So just like, I think it was relative atomic mass, relative isotopic mass, relative formula mass, there's a bunch of these that have a lot of the same words in them. You just got to find what's different. So standard enthalpy change of reaction is the enthalpy change where you have your amount of reactant react to give products under standard conditions. So enthalpy change of reaction is, in its simplest form, the enthalpy associated with reactants turning into products, because that's a chemical reaction. And what's the keyword that's going to be there in every single one of them? That standard conditions, right? Put those standard conditions there. There's probably a mark associated with it. All right, second one, enthalpy change in formation. This is the enthalpy change when 1 mole of some kind of compound is formed from its elements in their standard state. So an example of an enthalpy change in formation, give me a chemical compound, and don't do it too complicated for your own benefit. Any chemical compounds. Calcium oxide. I like your thoughts because, you know, the more complicated, the more work we'd have to do. So calcium oxide, to form 1 mole of calcium oxide, What are the elements that form calcium oxide? Calcium and oxygen. So you would write calcium and you would write plus what?
O2.
O2. So the standard enthalpy change of formation is the energy change associated with making CaO from the elements that combine to make it, right? In the first place. And so it's not balanced. How would we balance it? Nope. Nope.
Put a half in front of the oxygen.
Yep. And so remember I told you earlier in the year when we were balancing and some of you were like, I told you there'd be a time where you have to use fractions. It's here. Because what does it say in the definition? You must have 1 mole, which means this is a fixed number, which means you have to have 1 calcium on each side and you have to have how many oxygens on each side. So this number is then 1/2. Does that make sense? So in order to calculate the enthalpy change of formation, you would need to use this data. It has to be like this. Okay, and then combustion, last one. Enthalpy change when 1 mole of a substance is burned. Hey, what can we burn? Organic materials, right? So something organic. We've done that unit. Give me some random organic material. And again, not too complicated, please. What'd you say? Butane? Sure, why not? All right, so we're going to burn some butane, which is exactly what's in our burners, right? So we got some butane. What do we have to react that with?
O2.
O2, and we have to make that into? Well, we assume that it is a complete combustion, so it's going to be CO2 and H2O. All right, what's next?
Oh, no.
You balance it, right? So this would be a 4, this would be a 5, and then what?
Then you put a
5 plus 8 is 13.
that's what I meant.
Wait, 5 plus what?
Oh, 5 plus 8 is 13. And this would be 13 over 2, or 6.5, right? If you're fraction phobic. But the requirement is this has to, according to the definition, for us to calculate an enthalpy of combustion, 1 mole of substance is burned. This is a fixed amount of fuel that you have. It is 1. So this is actually important in the definition because it actually goes to the equations we're making as well. And so notice what's the same and notice what's different. In every one of these enthalpy change definitions, it's the energy change, right? That's in every one of them, right? The energy change. What else is the same in every one of these definitions? Standard conditions. So what actually changes in the definitions?
The amount of each.
For reaction, you got to know it's just reactants to products. For formation, you got to know it's elements in their standard state 2A,
Mole of
1 mole of a compound. And then for combustion, you know it is 1 mole of a substance, some kind of compound that you're burning to make the carbon dioxide and water. They do expect you to note that it's excess oxygen. Why is that important in the definition? Right. So you have to include excess oxygen in that definition because if you don't, instead of making carbon dioxide, you're making carbon monoxide. And I don't know if you were watching the news last night, but sometimes I watch the news. And they mentioned that, I don't know where it was, but it was in South Florida. There was actually a house that had carbon monoxide poisoning in South Florida, like yesterday. And they had like the EMTs and everything because people like passed out. So. I didn't get that far. I was too tired. I fell asleep.
Just to put in the story.
You can go look it up. It's probably on the, I usually watch Channel 7. It's probably on Channel 7. Anyways, but it was like, that's the reason. Just to throw it out there. That's why you gotta have excess oxygen in your definition. Because we're trying to do complete combustions and not make carbon monoxide. Make sense? All right. So, definitions. We got through that standard. Ready for calculations? Beforehand, this is how you see it in equation form. I've already mentioned this. So let's go ahead and take a look at something. Let's take a look at some reactions. Can we classify them as what they are? Does this reaction describe an enthalpy of formation? Yes or no? This first reaction.
No. It's a reaction.
No, yeah, that's.
So for it to be delta HF, what does it mean it has to happen? Elements to
Compound.
compounds. Is that what you observe in reaction A? So that ain't it, the thing. Delta HR.
Yes.
In order for a reaction to be allowed to be called a delta HR, reactants have to turn to products. Listen to that again. In order for a reaction to be called a delta HR, reactants have to turn into products. You should think about this. Like, I know you're all tired. It's Friday. It's the last class, and you all had a rough week. I'm so sorry, but think about this. If we have a chemical reaction, don't reactions turn to products like every time? So wouldn't every reaction technically be allowed to be called a delta HR, like as like a mating? Yes, every single one of these is a delta HR, but some of them can be classified as more than that. So far, so good? Because every single one of these changes is reactive to products. What about combustion? What's the requirement?
CO2 and H2O.
Fuel plus O2, right? Something you can burn. You burn it. So,
All the ones in the last one.
delta HR. Is there anything else that this can be, or is this just the delta HR?
Just a delta H.
That's it. Second one. Is the second one an enthalpy of formation?
Yes.
Yes. Carbon as graphite is its standard state. That's how we encounter natural carbon, is graphite. Oxygen is O2? Yes. Carbon dioxide is compound made. This is elements in standard state go to compound. This is also delta HF. Is this a delta HC?
Yes.
Yeah, final answer, right?
It is. Because you took something and you mixed oxygen with it. And that technically, if you go back to what it says here, yeah, oxidations are technically combustion. By definition, an enthalpy changes, right? It says 1 mole of substance is burnt in excess oxygen. So some kind of substance, you've got oxygen with it. That makes it combustion. This is like 1/2, like this is 1/2 of the story, this is the other half. But this is a delta HC. Wow. Next one.
Delta HF.
Is it because these have to be elements in their standard state?
Oh, so it's
Is this
HR.
an element in its standard state? So can this be a delta HF?
No.
No. Can it be a delta HC? If it ain't got oxygen, it ain't a delta HC. So it's just delta HR.
Oh,
Next one. Is this delta HF?
Yes.
Yes. Yeah, we're good with that? Element standard state, go to water. Delta HF. Okay. Is it a delta HC?
Yes.
By definition, it's something you could burn that. This is actually, have you ever heard of I might have mentioned before, a hydrogen fuel cell? Hydrogen fuel cell is what they use as an alternative energy to fossil fuels, where you burn hydrogen, which we know can explode, right? With oxygen, and you make water, which is clean energy. A lot of scientists are working on that type of clean energy with fuel cells. There's danger associated with it because hydrogen is explosive, but it is totally a combustion. That's the equation of a hydrogen fuel cell. What? So when you break up the atoms, they're really attracted to each other. H like this is crazy unstable, and so to break it apart, it actually explodes. That's why it's explosive. Hydrogen bomb is the actual, yeah, it's but it's not from a chemical reaction, it's from a nuclear reaction. But they use hydrogen in the hydrogen bomb, yes. All right, good so far? So this first thing was to be able to look at a reaction and classify what type it could be identified as. So this means Cambridge can be spicy with you, and for a reaction like this, they could call it any of the three, and you have to recognize that. So let's go to a paper one. Paper one question. Which equation, to the best of your ability, would you say represents the standard enthalpy change of formation of ethanol? C2H5OH. You are correct. So what are we looking for? The standard state of carbon, the standard state of hydrogen, the standard state of oxygen. Actually, which one is it? There's actually one wrong thing in here. I didn't catch this. Is ethanol a liquid or a gas? Ethanol? It's crazy that they ask you to expect this, but I think I don't say. Ethanol is alcohol, right? What's the state of matter of alcohol? Liquid. So you can actually take C out just for that. At standard conditions, alcohol and ethanol is wood alcohol. It is also the alcohol that people drink in lower concentrations. That is the alcohol people drink. It's called ethanol. Now, what is the right answer? Why not A? What's wrong with A?
The standard state of
Carbon is not a gas. Carbon graphite is a solid. So D. Why is D not the answer? Carbon's still not a gas. And like this is crazy. Like look at D. They're telling you all hydrogens exist alone. Like hydrogen exists like that naturally. Like that's how they exist. And they're telling you that all oxygens just like exist like this naturally. Like that's how they naturally exist. Is that right? Government said D is crazy. Like, get out of here. The answer is B. And this is just them tricking you with because a lot of people say carbon emissions and they think carbon itself is a gas, but no. When they're talking about carbon emissions, they're talking about carbon dioxide. Carbon dioxide is a gas, not carbon. Carbon is either graphite or diamond. Both are solid. All right, good with this? Standard type of paper one question you could get here. Enthalpy of formation, enthalpy of combustion. Next thing, Hess's law. This is the math time now. So the total energy change in a chemical reaction we said was independent of how we get there. So it's independent of what we call the mechanism. It doesn't matter how many steps that reaction is. It doesn't matter how complicated that reaction is. All we have to know is what is the energy of our reactants and what is the energy of our products. And if we find the difference between those two numbers, that will give us the total energy change for the reaction. And that's what we're going to learn how to do now. Ready? So that's what I just said. Sorry. Like, I think I just said pretty much almost word for word that. But I'm pretty sure you all know that a lot of this is, I made these PowerPoints. Like, so sometimes the wording will be the exact way that I presented it unless I need to give you a definition from Cambridge. So if we know the enthalpy of formation of the products and the reactants, we can literally just subtract those two amounts, and that's this fancy little formula. This means sum. So it's the sum of your products minus the sum of your reactants, but this should be the element's standard enthalpy of formation. So you should put that little theta there. And that will give you the standard enthalpy of reaction. The sciences?
Yes.
What's it?
Math. He's cool. Trust.
He made that easier.
He did
Trying to do that
not make it
without
easier.
him.
I don't understand.
All right, so here we go. This is what Cambridge calls a simple energy cycle. And so what they are asking for you to be able to do is construct a cycle like this and then be able to figure out the math from it. So what you're going to see here is at the top are your reactants, go to products, your regular chemical reaction. And up here you have what we call delta HR, delta HR. Then you see these two other arrows. Elements in standard state, to be clear. Elements go to reactants and elements go to products. The elements going to the compounds in the reactant side is called a delta HF for your reactants. The elements going to the products is called the delta HF for the products side. And so what Hess's law says is that if you add these two arrows that go to the same place, you will get the equation that you need to solve the question. So what do I mean by that? This is the same place. These two arrows go to products and this one arrow goes to products. And so delta HF of the reactant plus delta HR for the overall chemical reaction equals delta HF for the products. This is an equation that the simple energy cycle, simple as Cambridge words, not mine, gives you. Rearrange this to solve for delta HR. What will you find?
Delta HR equals delta HF products minus delta HRF reactants.
Yeah. If you rearrange this equation, you're going to get delta HR equals delta HF of your products minus delta HF of your reactants. Isn't that the formula that I already showed you, just without the summation signs? So these energy cycles prove the formulas that you'll use to solve questions. Now, in America, when I was studying chemistry, we only memorized this. We never did an energy cycle. But for Cambridge, for the international curriculum, you actually may be asked a question where you've got 3 points and they ask you to fill in an energy cycle. So I'm going to show you how to do that. But it leads to the same formula. So the idea here in Hess's law is that you can construct from 3 separate reactions. You can make an equation to calculate the delta H of a reaction. This is a reaction from elements to reactants, standard state of elements to their reactants, standard state of elements to their products, and then the overall reaction. All right. So, something important here. This is that same formula again. If you're not asked for an energy cycle, by the way, and 90% of questions don't ask for energy cycles, 90% of them. If they don't ask for you to make a cycle, guess what you can do? You can just memorize this and get your answer. Add up all your products, subtract all your reactants, you're going to get the energy change for the reaction. But there's a key thing here, and I bolded and underlined it, which means you better know this or life is going to be very hard. The enthalpy of formation for an element in its standard state is 0 because the energy change, let's say to go from O2 gas from its standard state of O2 gas would be what? What would be the energy change to make this happen? 0, because there is no change. So what this sentence says is that if you've got an element and it's in its standard state, there is no change in energy. So the change in energy is 0, which means you're going to plug in the number 0 when you see an element by itself in a chemical reaction. And I'm going to show you how to apply that in a little bit. But does that concept make sense? If the definition of delta HF is this forms from that, but this is the same, that thing, there is no energy change. All right, so let's take a look at our first checkup question. First thing to do, they ask us to draw an enthalpy cycle to calculate delta H. So there is a possibility you could be asked, it's in the objectives, to draw an enthalpy cycle. So we need to get the idea of what to do here. Remember that it's going to be reactant here. What comes after the arrow?
Product.
Product here. And then at the bottom is elements in their state. I should read that again. Elements, standard, state. And then it's the reaction of the elements to the reactants, the elements to the products, and that's what you got. And this is delta HR, this is delta HF, and this is delta HF, the formation values. Now, what are the identity of my reactants? Do I know what that is? Literally copy paste. You've got the reaction. These are the reactants and these are the products. So far so good? So 2AL, I'm not going to fill in first space, but reactants. What are my products?
F2FP plus L2.
And then you have to now think a little bit. What are the elements in their standard state?
Aluminum and iron.
Right? It is important to note it should be balanced. So how many aluminums are in this reaction? How many irons? Was there another element besides aluminum and iron?
Oxygen.
Yeah, I should have had more space. O2. What number should I put in front of O2?
1.5.
1.5. Thought I heard enough. I guess I didn't. So if you see this, it shows up on a paper too. It could be worth around 2 or 3 marks. I'm telling you just based on what I've analyzed. It doesn't often show up, but it can, yes.
Why are you putting
To balance the equation. So it's balanced the whole way around. So this is a reaction to this, right? This is a reaction that goes to that. There are 3 oxygens here. This is O2. O2, 2 times 1.5 is 3. Just like I had 2 aluminums here and 2 irons here, the amounts have to be the same everywhere.
So
Yeah.
That's for both.
So energy cycle should be balanced. Just make life easy. Let's draw an enthalpy cycle to calculate delta H for the reaction. So what is the calculation then? Literally the same formula. It's going to be delta HF reactants, right? So we do this. Delta HF for the reactant plus delta HR equals what?
Delta HF for product.
The other arrow, right? They go to the same spot, so you have to add, this is the arrows on the one side, and this is the arrow on the other side, which is delta HF for the products. You're solving for delta HR, so what do you have to do? Just calculate delta H for the overall reaction. You have to move reactants to the other side. Now, because this is delta and delta HF question, do you really have to do this, or could you just memorize the equation? Because we keep getting the same answer over and over. Again, you can just memorize the equation. So this is the equation we're going to use to solve. To find the enthalpy of reaction, we're going to need the enthalpy of formation of our products and the enthalpy of formation of our reactants. Now, there is good news here. Going back to the title of the lesson, theoretical energy calculations. In order to get the delta of your products, they're going to be provided to you. You're going to get the numbers for your products. You're going to get the numbers for your reactants. They're going to give you, like, for example, you're going to see it in your slides, iron 2 oxide. What is its delta HF? It's going to be provided. And you just have to do the calculations, like input the numbers in the right spot. You ready to see it? This is it. On the next slide. So it says, calculate the enthalpy of that reaction using using the information. So they've given you the numbers. And so we know that it's the enthalpy of our products minus the enthalpy of our reactant equals the enthalpy of the reaction. So, well, how do I know it's my product and how do I know it's my reactant?
The last slide.
So I'm going to rewrite it at the top here. So it was 2 aluminum
Plus.
plus
Fe2O3.
Fe2O3 goes to 2Fe plus Al2O3. Okay. So, by far the easiest way to do this, and first of all, I want to bring up enthalpies of formation are given in what units?
KJO.
How many moles?
1.
So this is stoichiometry. Like, do the molar amounts in the equation matter?
Yes.
If it says, I mean, in this equation, it's 1 mole of each, so it's fine. But what if this number in front of Fe2O3 was a 2?
Yes, multiple.
You would have to multiply by 2 to get the total amount of energy, right? So here's what we're going to do. We find the enthalpy of formation for our products. What are our products here? What is the enthalpy of formation for Fe?
0.
Good job. Because iron's in a standard state, right? So the enthalpy of formation, the delta HF of this is 0. 0 times what?
2.
Right? Isn't it 0 times 2?
Well, so 0.
I have a point. If it wasn't 0, you would have had to multiply by 2.
Yeah.
So this delta HF is 0. So far, so good? What is my delta HF for aluminum oxide? If it's a compound, are they going to provide you with the number?
Yes.
Yes, unless they're asking. Like, they give you the delta HR and they ask you to rearrange the equation to, like, solve for that. It's just like math. You're going to be asked for one thing that's missing in the equation. So Al2O3, what's the number?
Here's 1675 7.
Delta HF equal that 0.7 times what?
1.
Technically times 1, right? Because you have to multiply by the amount of moles in front times 1. But that's going to be, as we know, the same thing. The delta HF of this is negative 1675.7. So then, if you'll recall, the actual formula is that we have to give the sum of the delta HF of the product, right? What does that mean? These two numbers have to be
Added.
added to
Each other.
each other. So what's 0 plus negative 1675.7? And I know it sounds silly, but I'm just saying this is the procedure you gotta follow. In this case, it's just negative 1675.7. Are we okay with that?
Yes.
No? 0 plus 1. 1 times that is
Yes.
0 minus 1675.7 minus 1675.7. Yes? So our delta HF of our products is negative 1675.7. Yes? Subtract the enthalpy of formations of your reactants. Can we get those numbers for the reactant side now? What's my delta HF of aluminum?
0.
And I write it right underneath. Yes. Go, my pass? Yes, where's my pass? I'm confused. Oh, it's here. I just need it. Yeah, you can go. It's here. Just bring it back. 2 times 0, right? Or 0 times 2? We're good with that? Equals 0. That's the enthalpy of formation of aluminum. What is the enthalpy of formation of Fe2O3? They tell you it here. Negative 824.2. What do I multiply that by?
1.
1, which is the same number. So I have the delta HF of Fe2O3 is negative 824.2. So what does that mean in my calculation? I'm subtracting, right? The addition of my enthalpies of formations of my reactants. What is 0 minus 824.2.
Negative
Respect the sign. So it's negative 824.2. But what if I had to subtract negative 824.2?
You would add it.
Because this is a subtraction, right? Double negatives will be here. The formula is a subtraction. So whatever the sign is here, you're actually just gonna flip it to the other. And this is gonna equal our delta HR. So to get our answer, what do we do now? Math it. Negative 1675.7. What's the math? Remember, double negatives multiplied by each other become a it sounds right. I get negative 851.5. Negative 1675.7 plus 824.2 equals negative 851.5. Let's just change this to a plus and then put those two together. And what's the correct unit? Always. Someone is out. They just left. You'll be next. Yeah, you can. All right. How do you feel about it? Yes.
This would be on the test.
Wait, negative one where? It means the same thing. But yes, this is the best Cambridge way to put it. Like in the bell work, that's the best Cambridge way to put it. Because it's the same thing for math. A division by something means raised to the negative 1 power. We'll talk about that more when we get to a discussion on units later on this unit. But yeah. But notice how it was presented to you here. KJ slash mole, so K slash KJ slash mole. You would see KJ mole minus 1. Like in the lab, you saw KJ mole minus 1, so you should answer in the way that they present to you. All right, ready for another one? Let's try again. This time they don't ask you for an energy cycle. They give you the enthalpy change information of these things. They tell you a reaction. They give you the chemical reaction. Then they ask you what is the value of the standard enthalpy change of reaction. So what can we do here? Just from the last one, what did I do? What did I really do? Think about the steps. I wrote a lot, but whittle it down to what are the things I really need to do. Think about it. I need to add up the delta HFs for my products. I need to add up the delta HFs for my reactants, and what do I have to do? Subtract them from each other. That's really what the process is. You've got these fancy formulas, but the process is always the same. So, and then NO3, I'm just going to read this left to right now. What is the enthalpy of formation for this thing? You got to find it in your words.
696.
Negative 696. What do I need to multiply that by?
1.
The same thing. Like, that's what that is. That's my reactant. That's all I got on the reactant side. So what are my products?
Negative 5.
So delta HF reactants is this. MnO2 is
520.
negative 520. What do I need to multiply that by?
1.
Do I really have to write that?
No.
No. I'm only saying it to prove the point for when it matters when the number's not 1. What is the correct technique? So negative 520. But I have another product. What's my other product?
33.
33
Divided by 2.
multiplied by 2. So actually
66.
plus 66.
34.
And then combine these two together. Yes? Because all your products, you have to add them all up with each other. So you get negative 520 plus 66 is negative 454. So far, so good? So that's my delta HF for my product. Now to get my delta HF, my reaction, what do I do now?
Subtract those. So add.
So where can we go horribly wrong?
Subtract.
With our signs, right? So just be careful. Remember, it's to get the reaction, it's the delta HF of the product minus the delta HF of the reactant. So plug in the numbers. It's negative 454 minus. So what does that end up being?
Was it 242?
Yes. And that's the answer. And that's see it? All right. Questions? Are we good with the second example? Always products first, reactants second. Products minus, reactants. Where does that actually derive from? This is officially Hess's law here. So it actually comes from the energy cycle. Yes, you're next. All right, welcome back. Take a quick picture. Ready for another one? Kamani, make sure to take a quick picture. All right, how much do your brains hurt so far?
Not that much.
A little bit? A lot of it? What? Have you been okay with absorbing this concept? That's a yes and a no at the same time. Understood. Okay, we're gonna do another one. Need to know for pacing. All right, here's the next one. The next scenario, what paper is this from, by the way?
Tip 2.
This is the paper 2. And so they give you the standard enthalpy changes of formation of ammonia and water and steam. And then they say use this data and the value of delta HR given below. They're telling you here this is delta HR. That is delta HR. To calculate the standard enthalpy change of formation of NO. Uh-oh. What are we being asked for here? Of what? We're not being asked for the overall enthalpy of the reaction. We're being given. We're being asked for one of the products. What does that mean we're going to have to do math-wise? Algebra, right? So the first thing you're going to have to do is figure out everything you can. What is the NH3? What's the number for NH3? So we're going to know that this is negative 46 times 4, right? What's negative 46 times 4?
Negative 184.
Negative 184. And then we still have to add that to that oxygen. What is the standard enthalpy of formation of oxygen? 0. Oh, 0. So this is the delta HR, the delta HF of the reactant. Are we okay with that? Now for the products. What is the delta HF for NO? So what would we call it if we don't know it?
Question mark for X.
4x.
4x. It is 4x. Let that marinate. I'm looking for NO, for one NO, because it's the kilojoules per 1 mole. So we have to call this 4x because there's a 4 in front. All right, what about H2O gas? We got a number for that?
142 times.
It's negative 242 times 6, which is,
Negative 452. Negative 1450.
so it's 4x minus 1,452. This is my delta HF of my products. Right. So the formula is delta HR equals the delta HF of your products. Doesn't matter where you write. This is just me HF of my reactants. I have my enthalpy of reaction this time. It's algebra. So I have that that's negative 906. For the products, I have to plug this in. 4x minus
4x minus
1452. And then subtract what's here, which is negative 184. All right. So the goal now is to solve for F. Right? Solve for F. Correct. That is correct. So it's time for algebra. 4x. This changes to a positive, right? So it becomes negative 1452 plus 184, which becomes negative 1268. Add that to the other side. Negative 906, yes. David, after David comes back, we could. So it's, I get 362 equals 4x. Divide by 4, divide by 4, and your answer is?
9.
Okay. Now, where will Cambridge be very stingy here? Because 90.5 is actually not going to give you all the marks.
We have multiplied by 4.
Enthalpy,
Oh, negative?
positive. Respect the sign that you got positive, right?
Oh,
But you literally have to write positive because it's an enthalpy value. And you have to say this is an endothermic process. Okay, so looking at the time and thinking about your brain cells and knowing what's on the Cambridge test you're going to get next week, I'm going to stop here because there is another thing to cover, but I'm going to wait to cover it until the next lesson, which actually is crazy. It's not going to be until like 2 weeks from now because next week I only see you all once, and that's for the test. So for the I'm going to tell you something right now. I will write it on paper. For the homework, double checking it. There are no questions, it looks like. I think this happened last year too, that have this topic. So therefore, you can still do the homework based on what I have taught you in this lesson. The other enthalpy cycle, I'm going to teach you when we return in the next lesson. So, but will this show up on the test possibly on Wednesday?
yes.
Yes, so you guys got here. Do the homework, it's due Tuesday night. I will be here for tutoring, test review tutoring on Tuesday after school. Test review tutoring on Tuesday after school. For the exam next class, and we're done for 2. Don't forget your labs. You've got 10 minutes if you needed to revise something or ask me a question about your lab.
Oh, you're saying
There you go. I'm gonna pass it out the rest. Oh, yeah. How'd it go? Yeah, extension, no? And then either.
I do all global work. I did global work.
Alright, so take this one, I'm gonna give you how many marks are on each.
Because when I start counting, it's very embarrassing now. It's gonna be my second
All units though will be on the,
Well, you guys all see me how Christmas.
alright.
Understood, but I didn't I was told that too.
I don't cry. I cry like
You can cry.
That's what we're saying. Like,
You know how sad it is?
A singular noun superior.
yeah. All right, let me get the door real quick. Julia, are you next for the restroom?
Yes. Yeah. I don't
You
want
did.
every class. No, I'm kidding.
All righty. Julio, you're next.
We both kind of together.
Whoa. Gracias.
De nada. All right. Did you have a question next?
All the pressing before the better ones.
So the reason why they're giving you this is because 1H plus will make 1 more. But this will only have 1H plus. It actually has 2H plus. What? And so there will always be double the amount of water than there is of fluid. So the number on the bottom here is actually 8.05. Oh, you can. No, this is because this is a diperic acid, what that means is there's 2H plus. And if there's 2H plus and already 1H plus, that means there's double the amount of water produced from the amount of H plus. Yes. They are asking you.
Oh, I definitely failed. If you need to play the I was only able to do I was only able to complete 6 questions. A lot more than 6.
Good afternoon, Gold Lions. This is the car
I can tell you that. I have to find it yet, but this is that's good to find it, but it's definitely not the answer. Like if it ends up sort of an activation of the trip, it's not good. Like it could be still a choice to exist, but it's not. Because we have more. So I wouldn't give you a choice for that.
This, I think you forgot to give.
Oh, okay, okay. Where I gave one.
Yeah. You didn't give it to me.
Uh-huh. Uh-huh. I got what happened. I got it.
The south side of the building is not accessible until emergency.
That was my vote. You said for one. I said if you do, you should keep that. Was my vote.
I don't say the best things that should be here.
No, somebody said that.
It's gonna help others.
Bless you. For me, yeah. That's it.
That's four.
Attention juniors and seniors. The Diesel Prize Ethics Scholarship. Ellie Diesel was a Holocaust survivor, worked tirelessly to draw attention to the genocide of Ireland. Use your experience in the same invention is called. Interested students should submit their essay to their English teacher by February 2nd, please.
Absolutely, go ahead. Please go. Go right
How
now.
did you get so? I'm actually real though. Like,
No.
Nobody's having. You show that.
I'm just done begging you at this point, please.
What else would you show? How accurate it is. Because it's never gonna be like perfect.
Well, you see this
And
guy, I
that's
want
what you
his
gotta
one.
learn is like we're doing
I think you're, and everything you know, you
I want to live. I want to live.
What if you pay for it?
I cannot take my I'm not gonna take money. How hungry are you?
I don't have my
I guess because students who come to tutoring.
Because the lunch wasn't lunch today. It's a choice.
All right, first come, first serve.
Yes. Oh, yes.
There's 4. That's literally first come, first serve.
We'll go halves.
Yeah. There's no more. That was,
Oh, you got.
and that reminds me of what is it? You Ryan from East Lake.
You were like 3 hands going for it, and I wasn't gonna like.
I didn't know.
So remember, on your 4th set of points, instead of donuts, pizza. On your 4th set of points, if you can get 4, you've just done 2. On your 4th set of Velvet, then it's pizza instead of 48 for Velvet.
You drop the water like every day.
We didn't get 2. We got 2.5.
It's like the 4th quarter.
Yeah.
Both got it. If you didn't get it, should have.
Yeah, you gotta get your Velvet right.
If I don't get it, should have.
2.5. That's what we got. Okay, so we got
Right.
these
Keep
2.
doing
No,
little
like
Velvet.
if I didn't get it, would you have shared half of yours?
It's not my fault.
A-levels first, they're still working on it.
I was right there when she said it first. I was all the way in front.
We're A-level, we're gonna beat A level. We're just better. Right?
I was rubbing George's face.
You're like, you can remember this. Be like,
Every time we get one more, I don't know something.
I don't know, I can tell you the pre-A classes this year are pretty strong. The pre-A classes this year are pretty strong.
We gotta take them up.
We're still
We
better.
gotta take them up.
Exactly. We're better. We're better. We're better.
We are better.
I can't compare because you were in pre-A, so I don't know how you learned.
Come on, you don't remember pre-A?
I don't even pre-A. You were.
I remember. Yeah, it's like when
I'm so
you
mad.
didn't see me, I was like, oh no.
You did all those experiments?
Yeah, all of
Oh
them.
my gosh, that's like,
I think it's like.
and then he also the kids almost had that didn't know he was there. I told those teachers, they were like,
There is one thing so for every
Doesn't make sense.
there. No, you'll always forget because of my teeth. I keep my teeth attached to my body so I don't forget them ever. The thing is, when you do so much, you have to minimize the amount of things that you could forget.
The good thing is that I don't get jump scared.
You don't?
You do get jump scared.
No, Mrs. Ware was I swear to God,
This
Mrs. Ware
is
jumps
no
everywhere.
way has a bread.
She jumps and it's horrifying. I just look behind me and
Study for the test. Next class, you got 5 days. Make sure you study. And tutoring Tuesday to review. Tutoring Tuesday to review. We obviously can't cover everything, but we'll review something. Bye. Enjoy your weekend. Bye. Enjoy your weekend. Hopefully. And remember, there's tutoring Tuesday as well. It's review for the test. Hi, Nick. Are you turning in some stuff for me?
Yeah, well, I turned most of them in on Google.
I see right now. I'm looking. You got a couple that I just see that are posted in my email. Because it always gives me a message. Oh, okay. Is that for you or for me? To keep track?
You can take.
That's-
I can take a picture of it. I mean, you can keep it just for like a little reminder. It was not intended, but I guess.
No, you can keep it.
Oh,
I get the emails, so we're good.
there is one little.
Okay.
Oh yeah, this one.
Yeah.
On one of the assignments, you said specifically this one. You said not to do
2,
question
3, 4. If I recall.
2, 4. Yeah.
Oh my God, that page is upside down. Crazy.
So that's.
You didn't have to do this one.
I know, but this one is the exact same.
That's why I said you didn't have to do it.
Oh.
It's because you only have to do it on one of them, not both of them.
Right. So that one
So
was the only.
for this one, you don't have to do it.
Oh. No, that one. But this, it was the.
Yeah, so for this one, you don't have to do it.
Yeah, and this so
That
this,
one you do.
this is for this current one,
That's in the current unit, yeah.
the unit 4 homework 6.
It's the last homework, pretty much.
Okay, all right.
This
So
is the
then,
last one that you have
so
homework
this
on.
is actually the one that
Yeah,
I had to take.
that you
pictures.
have to take pictures of
All
and
right,
turn
then
in.
I'll do that. But the rest of it is good.
Okay.
I just wanted, like,
Thank you, Nick. I posted the answer key last night. I was working on it and then I posted it, but I'm not gonna be able to grade the test until Monday. So I put up the answer key so you could like check it yourself to see like what you got and what you didn't get. If you remember like which topics and study the ones you don't, because I put up the test with an answer key, but like with most of the questions solved out, like how it was solved. And then I'm gonna put the grades in the grade book on Monday. And then remember the quarterly itself is on Tuesday. And no notes for that one. Bye. You too. I can't continue. Too tired. She was really just. So the in this back. Rude. Which is fine. Let's do this.